Hi everyone, my name is Guilherme Ottoni and I'm going to present our paper HHVM Jumpstart, boosting both warm-up and steady-state performance at scale. Virtual machines have become a very popular mechanism to implement high-level programming languages. Typically, high-performance virtual machines compile the code in two steps. First, ahead of time, they compile the source code down to an abstract representation typically called a bytecode. Bytecode is what actually gets deployed, and then at runtime, this bytecode is compiled down to machine code via just-in-time compilation. Compared to purely ahead-of-time compilation, virtual machines have a number of advantages. First, they're more portable because this bytecode representation is machine-independent, so it's easier to execute it across a variety of different platforms. Second, virtual machines are also more scalable, especially for large-scale applications, because this bytecode is higher level and much more compact than the actual machine code that it's going to get compiled down to. And finally, because the compilation to machine code is only done at runtime, the JIT compiler is a lot more capable to leverage runtime information in order to produce more efficient machine code. And this is particularly important for dynamic languages because they have a lot of dynamic features, including dynamic typing. And in lack of accurate type information, the compiler has a hard time generating efficient machine code. Despite these advantages, virtual machines also have some disadvantages. And mainly, they come because of the runtime overheads introduced, particularly during the warm-up of the application. So there's a lot of profiling and just-in-time compilation happening while the application is executing, which actually adds a lot of overheads. So in this work, we actually tackled trying to reduce some of these overheads during the warm-up. And we studied the warm-up of virtual machines in the context of HHVM, the hip-hop virtual machine, which is an implementation of the PHP and Hack programming language that we built at Facebook. And HHVM is not used just at Facebook. It has also been used to run a variety of other websites, including Baidu, Wikipedia, Slack, and more. And we think that HHVM is a great case study for the warm-up problem in virtual machines in general because of a combination of factors. First, it implements a dynamic language which leverages a lot of, which can benefit from a lot of runtime information to result in better compiled code. Second, HHVM uses a lot of state-of-the-art compilation techniques, and it's also a highly optimized system with production quality. The problem of warm-up in HHVM is common to other virtual machines, but it is also exacerbated in a large-scale deployment like what we have at Facebook. So for us, the challenge is bigger because of a couple of factors. First, the source code of the application that's running is very huge. It has more than 100 million lines of code. Also, this application is constantly being updated and also constantly being deployed. Every 75 minutes or so, a new version of the website is deployed, including thousands of changes. So now imagine every 75 minutes, we are deploying this very large application, and at runtime, we're doing profiling and compiling it down to machine code. So that can add a lot of overheads. And this is even more important once you're running a very large scale deployment with a very large number of servers, which is just multiplying this cost by a very large factor. So here's a diagram illustrating how HHVM used Warmup prior to this work, prior to Jumpstart. And at the bottom, I have a graph plotting the amount of JITted code also that is produced by the virtual machine during the execution. So the server starts by doing basic initialization, and then it starts to take some user requests. And once it starts to execute this request, it starts to produce compiled code in profiling mode, which is going to gather a lot of runtime information that's necessary to produce more efficient machine code later. So this happens until point A here, when the JIT stops to produce profiling code and then executes that for a few minutes to collect profile data, and then which ends at point B here in the chart. And based on that profile data, then the JIT produces optimized machine code, which it finishes around 10 minutes in point C in the chart. And after that, new code that is reached, it is still compiled to machine code, but it's compiled in a live mode that we call, which doesn't leverage profile information, but it's still able to inspect the live state of the virtual machine in order to gather type information and some other information to still produce decent machine code. And this happens until point D in this chart when we fill up the code cache of the system. And at that point, we stop producing new JIT code, and any new code that's seen at that point is just run through an interpreter. So overall, we can see here that the entire process takes about 25 minutes until we reach point D, where the system reaches its peak performance, and the JIT ends up producing nearly half a gigabyte of code. So now let's have a look at the impact of the warm-up on the server capacity. So here's a chart illustrating the throughput, or the number of requests per second that the server can handle over time during the warm-up phase. So you can see that at time 0, once the server restarts, it cannot handle any requests while it's doing initialization, and then at some point it starts to take user requests, but this curve slowly ramps up because of all this compilation and profiling that's going on as well. Over time, after about 25 minutes, the server reaches its peak performance again, peak throughput, and the area under the curve here means the total number of requests that the server was able to handle during that warm-up phase. And the area above the curve means the lost capacity, or the number of requests that the server could not serve because it was not fully warmed up yet. So in order to address this warm-up problem, we propose this technique that we call jumpstart. Jumpstart actually builds on previous work that proposed to share profile data across virtual machine executions. The problem for us here is that different executions of a VM on the same server, they actually have a very different version of the source code because, as I said, there are thousands of changes that are going in between two consecutive deployments of the virtual machine. And because of that, a profile data collected in one instance of the VM to the next one can quickly have degraded profile quality because of all the changes that are going in. So with Jumpstart, what we did is actually was to share the profile data across different servers and only between instances of the VM that are running exactly the same version of the source code. In order to do that, we leveraged a phase deployment for the Facebook website, which actually was already in place before, and which is also common to large-scale deployments. So if you have a very large fleet of servers running an application, you don't want to update that all at the same time. What we do is you roll that out to a small portion of the fleet, and you monitor that for some time. In our case, we roll out to 2% of the fleet, and monitor that for about half an hour until we verify that everything is good and deploy to the rest of the fleet. So basically, we leverage that in order to improve the warm-up of the majority of the fleet as well. So here's a quick diagram illustrating how the server is used to warm up across the entire fleet without Jumpstart. And we see that all the servers were going through this red phase where it's actually doing all the compilation and profiling, and the performance was not great until it was able to collect profile data and produce optimized code, and then reach this green phase where it was running at a much higher throughput. With Jumpstart, this profiling only happens in a small fraction of the fleet that collects the profile data, and then this data is spread across the entire fleet so that the majority of the servers can actually optimize codes right from the beginning and then reach a much higher throughput much more quickly. So now let's take a look at the basic workflows for the servers that are both collecting this profile data that we call the seeders and the consumers of this profile data. So for the seeders, the workflow is actually very similar to what we had before prior to Jumpstart. After initialization, the servers start taking user requests, and you start to compile profiling code for that code and then collect profile data. But then instead of optimizing the code based on that profile data, it just serializes this profile data to a file, and then it exits to do some basic validation of this profile data. On the consumer side, the workflow is actually very different. After initialization, the server deserializes this profile data, and then it compiles all the optimized code using this profile data, even before starting to take any user requests. After that, it starts to serve user requests, and any new code that is seen is still compiled in live mode, like it used to do before, but the hottest portion of the code was pre-compiled before serving any requests. So in this work, we're also able to leverage jump starts to improve steady state performance, not just warm-up performance. And I should mention that prior work that proposed techniques to improve warm-up of virtual machines, at best, they were able to keep the same steady state performance, but they often degraded it because some optimizations had to be disabled in order to be able to share this profile data. In our work, we basically leveraged two different sources of opportunities to improve steady state performance. First, because profiling was not a bottleneck anymore, we were actually able to do more thorough profiling and improve the profile data that guided existing optimizations in the JIT. And second, because the profile data was available at startup, on the consumer servers, we're actually able to do some better decisions that affect the global state of the system, which are much harder to change after the system is already serving requests and has compiled code and so on. So let's take a look at some of these optimizations that we were able to do or to improve. And the first one is what is called basic block layout. And this is an optimization that actually we observed in our prior work on the bolt binary optimizer presented at CGO a couple of years ago, that it highly depends on the quality of the profile data. So it can actually benefit a lot from very accurate profile data that's collected on the final optimized machine code. So we already had this optimization in the HHVM JIT, but the profile data that was used to guide the code layout of the optimized code was derived from this profiling code, which looked very different and didn't have all the optimizations and had more instrumentations and so on. So what we did here was to actually extend this basic workflow that we had on the seeders to, instead of serializing the profile data right away, it actually produces the optimized code and instruments this optimized code with counters to collect the execution frequency of the basic blocks. And then we run that profiling code with that optimized code with instrumentation for a few minutes to collect this profiling data, and then serialize this as well along with the rest of the profiling data. On the consumer servers, the workflow is mostly unchanged, except that now, prior to doing this basic block layout, we go and read this profiling data from the serialized file, and we update the profile counts on the control flow graph before doing this optimization, just to make it more effective. The second optimization that we were able to improve based on Jumpstart is to sort the functions in the code cache. And this is also an optimization that we described here at CGO a few years ago, and which is based on a weighted call graph that has weights based on profiling data. And a problem that, so we had this optimization on the JIT already, but the problem that we had was, again, that the profile data was collected in this profiling code that looks very different from the final optimized code. And in particular, the profiling code doesn't do any function inlining, but the call graph drastically changed once you apply inlining. So what we did here was to basically leverage the same mechanism that we built to improve basic block layout and use the instrumented optimized codes to actually collect the caller callee frequencies that are used to update this call graph that we use to sort the functions. So those were two optimizations that we already had on the system and that we were able to make more efficient, more effective by leveraging Jumpstart. Now I'm going to describe a new optimization that was actually enabled by Jumpstart. So this optimization is to reorder the fields of the properties inside objects in order to improve data locality. And we want to do that based on profiling so that we can gather and group the hot properties inside objects, leveraging profile data. And a problem here that we had is that it's very hard to change this layout once the server is already up and running, taking user requests, and after you have compiled code that depends on layout of properties and so on. So what we did instead was to collect the hotness of the accesses of the fields or the properties inside the objects in the CIDR servers, and then serialize that with the profile data. And now on the consumer servers, once they start, before they serve any requests, when they're creating this metadata representing the classes, they can actually pick the best order for the properties to improve the data locality. Okay, so now I'm gonna move on to some evaluation, starting with some warm-up performance. And this is, for this evaluation, we measured HHVM running the Facebook website in production. And here's a chart similar to what I had before, showing the throughput over time during the first 10 minutes of execution of the server. So I have two lines here. The red one doesn't have a jump start, and the blue one has jump start. So we can easily see that with jump start, the throughput ramps up much more quickly, and the area under that curve is much higher, is much bigger, which means we have much higher realized server capacity. And the area above the curve gets much smaller with Jumpstart. That means we have lost, we didn't lose as much capacity. So overall, Jumpstart reduces the capacity loss by 54.9% for running the Facebook website in production. Now, for steady-state performance, we evaluated the speed-up of those three optimizations that I described earlier. And the one that benefits the most from Jumpstart is basic block layout, which kind of confirms the observations that we had made in the both binary optimizer work that found that optimization is highly dependent on the accuracy of the profile data. So basic block layout boosts performance of HHVM by another 3.8% just by improving the accuracy of its profiling, like we did in this work. And the other two optimizations, they still have a measurable but smaller impact of about 0.8% each. And overall, Jumpstart improves the steady-state performance by 5.4% for running the Facebook website. To summarize, VMs have a lot of benefits, but they also have this warm-up problem, which is quite significant. In this work, we described our Jumpstart technique to improve the warm-up of HHVM and of virtual machines in general. Jumpstart reduced the capacity loss for HHVM running the Facebook website by 54.9%. And at the same time, it also boosted the steady-state performance of HHVM, both by improving the accuracy of the profile data and also by enabling some new optimizations. And overall, Jumpstart improved the steady-state performance of HHVM by 5.4%. Now, I should also mention that Jumpstart raises some reliability concerns because now we have this profile data collected in one server that's spread to multiple, a very large number of servers. And in case there is a problem with that profile data or it triggers a bug in the JIT or elsewhere in the system, this can very easily bring down the entire website. So I didn't have a chance here to talk about, but we actually came up with a number of techniques to alleviate these concerns, and which we have implemented in HHVM as well. So I refer you to the paper to learn more about those. Finally, I just want to mention that we proposed this Jumpstart and implemented it inside HHVM, but I believe that that's a very general solution that can be leveraged for other virtual machines, particularly for large-scale deployments. So thank you. That concludes my talk. And if you have any questions, feel free to reach out to me at otoni@fb.com.